Well, thank you. I'm very glad to be here. And that was a very impressive talk we just heard.
I'm sorry, this can cut off. 1 second. I'm sorry about that.
Okay. So I'd like to talk about silicon hybrid integrated circuits. It's a collaboration of a bunch of students, particular Alan Liu and Art Gosser are doing the new work on quantum dot lasers I'll talk about. And then collaboration with Intel, Orion, and Hewlett-Packard. So I'd like to talk about 4 new things that hopefully many of you have not seen before. One is some recent work on the quantum dot laser work. Some is on integration of mode-locked lasers to get narrower line widths, less phase noise. One is on widely tunable lasers. And the final one is on 2D scanning lasers. And the goal here, it's a good example of just more advanced photonic integration. So there's more than 100 devices integrated together on these chips. So I think this audience doesn't need any motivation for the need for integration, reducing the size of this, and everyone knows that from Peter Windsor onward. And obviously for cases like this, you'd like to have tunable lasers, and so that's very much one of the things I'll talk about today. This is a slide from Orion and sort of the evolution of optical transceivers, but again, from where we are today to VCSEL-like solutions to integrating in a module. Again, integration is key, and this is cut off, but integration on silicon in particular is key, and so that's what our focus will be. So the goal is, how do you make 3.5 devices on silicon, basically, and take advantage of large wafer processing? So that's what I'll talk about. This is what Intel has put into a 200-millimeter fab today, all automatic wafer loading. It's very high volume, very low cost. The approach that we're using, is to bond 3.5 materials onto SOI wafers. So the optical waveguiding comes in the silicon layer. The gain comes from the 3.5 layer. And typically use proton bombardment, but we've also used lateral etching or oxidation to get current confinement as well. But proton bombardment seems to work the best. This is an example of what a 200-millimeter wafer looks like, where you bond the 3.5s where you need it. One big advantage here is that you can combine different epi together, and so we've done this. So some of these, like in Orion's post-deadline paper at OFC last year, might be 1310. Other ones are 1550. They're co-processed together. Other examples we've done are combining EAM dye with quantum well dye with some of Joe Campbell's very high current photodetector dye. So very different epi-layer structures can be combined together and co-processed all at once. And that's not something one can really do by epitaxial regrowth. And this is just an example of integrating a bunch of lasers together on one chip. So there's a good summary of this technology in JSTQE last fall by Mokhtar Heck. So here's the last overview slide, and then I'll get into new results. This is just a summary of some of the structures we made. Ring lasers, large ring lasers, small ring lasers, much lower thresholds. Work Di Liang has pioneered. DBR lasers, DFB lasers. I'll talk a bunch about DFBs later on today. We've made Mach senders, as well as EAMs. I'll talk a bit about the high speed, up to about 70 gigahertz bandwidth. You can make arrays of amplifiers with arrays of detectors for perhaps like extended reach configurations. And so that's sort of the past. What I want to talk about today in particular are going from quantum wells to quantum dots, and in particular from past work growing them on gallium arsenide to growing them on silicon and compare them to quantum well results. And then I'll talk about modulators, amplifiers, and detectors briefly. So we started doing this 20 years ago. Rich Mirren's thesis was doing quantum dots on gallium arsenide. So these are highly strained gallium arsenide dots. And this is an example of what was achieved back then. It was one of the first quantum dot lasers. Thresholds were not as good as quantum wells, but fairly high T0s, so showing the promise of quantum dot results. QD Laser has commercialized, obviously, quantum dots grown on gallium arsenide and getting very, very nice results. CW results up to 220 degrees C, high T0s. So that works quite well. They formed a company doing that. What we want to do now is take this and do it on silicon. So we like to go to larger wafers than you can get with gallium arsenide and then combine this with all the rest of the silicon photonics that we're all aware of. So at UCSB, this has gone on for a long time. Herb Kromer worked very hard on gallium arsenide growth in silicon back in the 80s. More recently, there's been really nice work at Michigan growing quantum dot structures, and in 99 was the first laser operation, first room temperature operation, 2005. Here's some of their early results. And this field has continued to progress. Nice work out of Arakawa's group at Tokyo, out of University College London. And in some of Arakawa's work, these are also Stransky-Krausnoff growth, like we'll talk about and Rich Mirren did. But now these are bonded to silicon wafers. So very much like the other silicon wafer bonding I've shown, but now they're making quantum dot lasers that way. This is the University College London work, again getting low thresholds and CW lasing up to about 30 degrees C. I'll talk about much higher results today, what we've recently achieved. So the goal here is that we can take large area wafers, and Motorola demonstrated epitaxial growth on up to 12-inch wafers. But there's a lot of issues, right? The polarity, thermal expansion mismatches are all very large. Our goal basically is to use the 3D confinement of quantum dots to mean that only a particular dot gets taken out rather than a region of the laser that's perhaps a diffusion length wide gets taken out. That's illustrated here. If you try and grow quantum wells on gallium arsenide, the dislocations mean that within a diffusion length in 2 dimensions, you get a reduction in gain, perhaps loss. Hopefully with a quantum dot on here, just one dot gets affected, and the neighboring dot, which may be just a tenth of a micron away or less, is unaffected. So these are some of the TEMs, and you can see dislocations. We still have a finite dislocation density in the active region, but we can still get very, very good results. So the structures that we're using were provided by IQE. So it's germanium growing on top of silicon. The silicon is grown off-axis so as to minimize the step antiphase domains. And our threading dislocation in the active region is on the order of 10 to the 8th. So the results I'll show on the order of 10 to the 8th. We end up using 5 planes of quantum dots inside an SCH layer. And Alan Liu, the student doing this, his focus has been to get higher densities than we've had in the past, and certainly much higher densities than what Rich Mirren had. So we're up to about 5, 10 to the 10, and trying to make them very uniform to get very narrow gains. This shows an optical photograph in SEM of what it looks like, but the morphology is quite good. You can make nice-looking devices out of these structures. And these are some of the results. So thresholds are fairly low. We've seen as low as 13 milliamps. This one's about 17 milliamps. But this one at 17 milliamps puts out 50 milliwatts CW. So it's actually quite a nice laser. The best results we've seen are here, 180 milliwatts output. So again, fairly low thresholds, but very high powers. Now this one's HR coded, and so all the light's coming out one side. And it is ground state lasing at 1253. So we do see the transition at higher temperatures, higher powers to excited state lasing, but we can get nice lasing ground state out of this. So to summarize, low thresholds on the order of 60 milliamps, high powers, CW lasing up to 119 degrees, and fairly good T0 on the order of 100 degrees Kelvin. So looks like a very nice technology, and we're now doing reliability studies to see if this idea that dislocations don't affect the structure like they do in quantum wells really holds up. Other work we've done, so this is now quantum well work. That's the end of the quantum dot work. That's very recent. It'll be presented by Alan Liu at OFC. Just came out in APL. This is a 16 DFB array where we've used quantum well intermixing to shift the band gaps and get gain over a very wide region. So in this way, you can have coarse WDM and still have multiple lasing peaks out of here. Then you can combine this with electroabsorption modulation and use quantum intermixing to shift the band gap of the modulators relative to the DFB lasers. You can make DFB structures. This is one example of one of the die that has a bunch of different designs on here. And we typically see good devices have yields of above 90%. The best devices, wafers, have had yields of 99%. And there's some variation in performance, so they're not by any means all uniform. But these, again, are fabricated at university laboratories, so it's not to be surprising. So now I want to talk about making tunable lasers in particular. And the idea here is it's an idea Bin Liu patented about 15 years ago of having two-ring devices, and these have different diameters. And so you have one Fabry-Perot free spectral range of this ring, and the other ring is different, has a different free spectral range, and consequently they line up on one wavelength. If you make a slight change, then it jumps all the way over to the next one, much like segmented grading DBR. And so this shows the multiplication of those two reflectivities, and then if you make just a slight change, it jumps over to the neighboring one. And this shows what experimentally it looks like. So in this case, they're overlapped here, and if you look at the two reflectivities, you can see that they get mismatched, and then they'll jump discretely. In terms of performance, they work reasonably well. This is about 340 kilohertz line width out of these structures, nice Lorentzian shape. Good side mode suppression, 45 dB. So the reflectivity does not show a huge difference, but it's enough that it laces only in a single mode, as you'd expect. And you get tuning over 40 nanometers, so wide tuning. And within one of these structures, you can get about 1/10 of a nanometer of continuous tuning. So that part works reasonably well. So we're using those now to make two-dimensional scanning devices. So this is an example of this that was presented last week at Photonics West. So over here, there's a grating. And over here is the tunable laser I just talked about. In fact, there's multiple tunable lasers, so one could generate multiple beams if you wanted to. And the idea basically is you've got the chip, and there's a gradient emitter. And as you change the wavelength of that, the angle of the light changes. And as you change the phase of this 32-channel in parallel, they're all necked down to this one gradient emitter. But these are the 32 gain elements, and there's 32 phase elements here. But as you change the phase of those, then you can change the tuning in the other direction. So you can make two-dimensional scanning with one of these structures. So this, by far, is the most complex PIC on silicon that we've made at UCSB, or I think anyone has made on silicon. These are early results, generation 1. This is a 16-element one without the laser integrated. And so this is with all the light centered in it here, and then this is the grading direction, so you get very good low side lobe level. The other direction, this is the 16-element phased array, and you do see side lobes. And of course, that comes because we have uniform spacing. So we are looking at, and Jared's talked about in his talk last week, about other spacings that you don't get the grading side lobes are much smaller. And then these are, if you tune it to the four corners, sort of how well that looks. And this is just an example. If you take line scans across that, you can get plus or minus 10 degrees, which is what we designed for. With our tunable laser, we can get 1 degree tuning resolution, and the line width is about 1.6 degrees. And of course, you can trade this off in different ways. The output power is about 2 milliwatts in the far field. So that's one example of integration. It's the most complex thing we have made. Other things we've looked at are making narrow line mode-locked lasers, and I'll talk about a few different structures, a few different examples of that. So here's one example. It's just a linear cavity mode-locked laser with loop mirrors at the end. And then we put basically a long delay line on one end, again with the loop mirror, so as to stabilize this mode-locked laser. And if you just passively mode-lock that, in this case at 10 gigahertz, by having this external cavity on here, you can narrow the line width down from about 1 megahertz down to about 15 kilohertz. So that's shown here. This is the mode-locked laser, typically what we see for a small, relatively short cavity length mode-locked laser. And then when you put the external cavity on, it gets dramatically smaller. So that's one example, and Mike will talk about that at OFC. Another general example of integration is shown here. In general, to get low phase noise, you want to make the cavity longer. But if you want to mode lock at a particular frequency, that goes the wrong direction, right? Long cavities give you low phase noise, but then it's highly harmonically mode locked. And that highly harmonically mode locked laser has a lot of instabilities because all the different pulses going around that cavity are all not linked together, right? And so one solution to that is to put a resonator in it. So in Peter Delphius' talk here last week, he talked about putting a bunch of discrete elements on an optical laser and bench and having resonators in the cavity so as to link these pulses together. What we're doing now is taking those examples and integrate it all onto a chip. So what I'll show is a couple comparisons. I'll show just a 20 gigahertz laser compared to a long cavity laser, 2 gigahertz cavity, and I'll show a 2 gigahertz cavity laser with one integrated with a resonated filter on here. And you'll see the dramatic differences in line width. So these are photographs of what the chips look like. They're actually made by Orion. And so this is just a long with a spiral delay line here. So it's 2 gigahertz cavity. And then this is the same thing, but with the short 20 gigahertz up over here, resonator inside the cavity. So if you just run this passively mode locked, this is what you get. So passively mode locked to the 2 gigahertz cavity. You see lots of wavelengths generated. You see this time domain autocorrelation trace, on the order of 30 picosecond pulse widths, which you expect for that long cavity, the dispersion in the cavity. And if you just look electrically, there's the 2 gigahertz signal. Fundamentally, though, we want to emphasize for our project, for DARPA, a 20 gigahertz signal here. So to do that, we can hybrid or actively mode lock that. And that's shown here. So you take this same laser, passively mode locked here, 2 gigahertz, 20 gigahertz. And now when we actively mode lock that, we get this strong tone at 20 gigahertz, and the optical spectrum narrows up a bit. If you compare this now to integrating the etalon inside the cavity, you see a much cleaner result, right? All these low-frequency spurs, 2, 4, all the way up to 18 gigahertz, are removed. And that's just because all these other harmonically mode-locked pulses are now linked to each other by this intercavity filter. And you see it dramatically in the optical spectrum analyzer as well. This is now spaced at 20 gigahertz spacing. As a second comparison, we can compare a 20 gigahertz cavity to a 2 gigahertz cavity with this 20 gigahertz resonator inside of it. And what you see here, again, just electrically, if you just run this passively mode lock, compare the two cases, you see dramatic reduction in line width, a factor of 30x. So again, that's just what theory expects and just what people show on an optical bench. We're just demonstrating this on an integrated structure. Just a couple more examples. So those were lasers integration. We've been integrating arrays of DFBs with arrays of modulators. We've gone through a number of generations. These are early lumped element modulators with traveling wave modulators with what we call segmented modulators, where there's multiple segments here and we adjust the impedances and lengths so as to remove or resonate out the loss of the microwave waveguide. So you can see that here. This is actually, the red line is what we predicted before it was made. And the normal microwave roll-off here is removed by these 3 sections that peak that up a bit. And the blue curve here is experimental results, but up to the 16 gigahertz limit of our device, of our measurement system. And again, if you look at this electrical absorption modulator, in terms of drive voltage, with 2 volts drive, we can get 18 dB variation. So it's not too bad. And this just shows it's back-to-back at 50 gigabit. That's the electrical drive, back-to-back at 50 gigabit, and then with 16 kilometers of fiber of the eye. So the last topic I want to talk about briefly, and then I'll sit down, is energy proportional computing. So a lot of people talk about the fact that the laser could be off-chip. It doesn't really matter. It's just a power supply. And I think that's a very flawed concept. And just like we need energy proportional computing inside data centers, so do we need it in photonics. And so the reason this doesn't work, basically, is that if you have an off-chip laser, it's going to all of the elements of the chip at all times, whether or not you're using them, and you can't turn off parts of the chip. The question is, how big a factor is that? So that's what this calculation shows. So we looked at 2 architectures, crossbar and butterfly architectures, and there's a lot of details in this paper. It was JSTQE last fall. But these are the results, basically. If the laser is highly utilized, right, so all parts of the chip are on, it doesn't really matter that much. The savings you get, shown on this axis, are relatively small. All you really gain is coupling from the laser to a fiber and from a fiber to the chip. However, if you're not running that all of the time, 20, 40%, then you actually gain a lot, not surprisingly. This is another breakdown of it for both the crossbar and the butterfly. Let's just take one example. The savings you can get, say at 50% utilization, which is probably pretty likely, is more than a factor of 10, right? It's more like a factor of 20 improvement. So part of it is the coupling loss reduction. Part of it is the fact that you switch off the lasers that you don't need. So that 50% of the tiles you're not using, those lasers get shut off. And then part of it is just the optimized design, the fact that you don't have to broadcast this laser power everywhere on the chip. So the savings are actually pretty dramatic, on the order of a factor of 20. This is one more example. This is an optical switch array. It's a 2D array. And this is how we do our electrical integrations. So we do CMOS at some advanced node. Our photonics is at some less advanced node. And the idea is we drop these chips in, and then we, with photolithography, connect all the wires up. And this is work that goes on with Luc Thigarajan's group at UCSB. And Louis Chen did this as his thesis. Maybe we'll skip this. So anyway, this is kind of a summary. These are all the photonic integration on indium phosphide with Infinera leading. This is their 1.6 terabit chip. This is integration on silicon. And that last example I gave you is actually sitting up here. So it was only published last week, but it's moving forward. There's a lot of challenges. We need to get lower thresholds than we've seen. We need to get higher gain in amplifiers, higher yields, better wavelength stability, isolator integration, and better CMOS integration of electronics and photonics together. So with that, our goal basically is combining silicon electronics with photonics together on a CMOS platform. And this is kind of a summary of where it stands. Thank you.
Okay, let's take one question or so. Is there any question in the audience for Professor Bowers? It looks like it's been very clear.
Great.
No, but on the modulation course, they go up to 67. What do you think would be the limit that you would go able to go beyond the results shown in your experimental curve?
So these are fairly short devices, which makes it easier. By keeping the links down to only 100 or 200 microns long, then the microwave loss in those structures is reasonably can be minimized. So we can really, I think, do 100 gigabit for sure. I think the more important issue is sticking within the CMOS driver constraints. So, that's 2-volt drive, which I think is possible with stacked CMOS designs. But we'd like to get, obviously, lower than that. And so that's probably the more important issue. I think that modulator would work at 100 gigabit if we'd love to collaborate with someone that has the driver to do that.
Very impressive.
So.